Continuing our discussion on heat, let's talk about heat and heat transfer. So in terms of energy transport, there's three ways that energy can be transported, either by conduction, convection, or radiation. Two of these require a direct medium, such as a solid or a gas, whereas radiation can pass across a vacuum. So here's what we mean by these three in a single example. If we were to have a fire, heat will radiate away from this in the form of radiation. It will impact this pan, where it will conduct through the pan, through the metal of the pan, and heat the water inside. As the water is heated, the hot water will rise and the cold water will descend, setting up convection currents and transferring energy by bulk movement of the material through the material. Conduction is actually indicated here because this pan will heat up, the pan handle will conduct, and eventually burn the hand of the person holding it, which would be unfortunate. So this is the way that convection really works in terms of water heaters and house HVAC systems. So in terms of the water, we will apply a flame to the bottom of this tank. The flame then heats the tank, conducts through, and then sets up convection currents, which eventually heats the water. The cooler water will end up descending, and the hotter water will end up rising. This is very similar to the way that atmospheres also operate, with cool air descending and warm air rising. The turbulence you feel in an aircraft is essentially caused by this exact effect. So if we look at our second diagram here of the house, this is how a simple heating system in a house might work. Here we have a furnace operating in this principle that we see here on the left, and this water is then circulated through a series of pipes into radiators, which then heat the air around them and cause convection currents to heat the room. The unfortunate part when we are dealing with heating a home is the warmest air is nearly always located on the ceiling, which is somewhat annoying if you're attempting to stay warm. So heat really flows by the mass movement of molecules from one location to another. This is convection. If we're talking about radiation, between, say, the sun and the earth, there is no medium as such. There are a few particles per cubic meter, but not nearly enough to translate heat. So as we said with the astronaut in space, the suit is required in order to maintain his thermal energy so he doesn't freeze. It's not that the temperature is low, it's that the density of particles is very low. So in terms of transporting energy, say, from the sun to the earth, this energy must move across a vacuum. And that's what's going on here with this solar wind. This is charged particles and radiation moving through space, which are then intercepted by the planets. They will hit the planets and they will then go into a pattern of convection and start to heat the planets through convection. But across the vacuum of space, they require radiation. And if you look down through a star, not to turn the whole class into astrophysics, you actually have convective zones in the cooler parts of the star, where hot gas is rising and cold gas is descending, and a radiative zone in the center, which is actually responsible for stopping this star collapsing and becoming a black hole. And then finally, we have conduction. This is motion of particles heating a substance. So for instance, put a spoon into a pan, and then heat the pan, or if you have some mixture or water in the pan, and eventually the spoon handle will heat up. So heat is conducted up the handle by molecules in the hand moving. We're going back to the half mv squared of the particles in the handle. So if you heat that spoon enough, they will gain enough energy to start flowing, and you could essentially melt the spoon. So in convection, we require hot gas to rise, which is less dense, and cool gas to sink, which is higher density. And that creates our heat currents. so things such as turbulence in atmospheres. In conduction, we require a solid body where the particles are moving around with greater and greater speed. And when we're talking about conduction, the thermal conductivity of different materials is shown here. So some materials are good conductors of both heat and electricity, things such as copper and aluminium, silver. These particular materials are good conductors, whereas things like cork, wool, air are poor conductors. And here's the various constants for this. So K is your thermal conductivity. Materials with large K are good conductors. Materials with small k are referred to as insulators. So if you were building a thermos, for instance, you would surround it with glass, which has a lower thermal conductivity, and then maybe put some kind of metal inside of it, such as copper or aluminium. So in terms of radiation, this is what I really want to come to. So with radiation, this is the transport of energy by packets of photons. So if you go outside and hold your hand up to the sun, you will actually feel your skin heating up. That's radiative heating that is causing that. And thermal radiation, of course, has become ever more present, especially in this age of the COVID virus. And if you take a look at this, you can actually see thermography showing where sick tissues are versus healthy tissues, and showing blood flow through a body. And as I say, with the COVID epidemic, we can actually see far more of these thermal cameras in places such as stores, and indeed here at the front door of Gannon. And here's the thermal camera, and you can actually see whether somebody is over a specific temperature or not. Here they're saying this person's, about 95, I believe. So in terms of light, in terms of radiation, we can really say that something like the sun is definitely the greatest provider of thermal radiation to the Earth. When we're talking about radiation, it will have an energy that's measured in joules. The watt is a rate of energy consumption or energy receipt. So this is how many joules you're receiving per second at some point. So a 60-watt light bulb gives out 60 joules of energy every second. So we have the joule and the watt. And this should be familiar to you from mechanics in terms of the concepts of energy and work. So when we're dealing with radiation and light, there are 4 ways that light and matter can really interact. Emission, so take something like the sun or a light bulb. These are sources which give out light. Absorption, an object near some lamp or something like that, if you put a dark object near a lamp, you'll feel it heat up. This is an object absorbing radiation. Radiation is incident on it, and it is absorbed into the material. Transmission, this is things like glass, where matter that allows light to pass through it. So something like glass, you'll see a bit of reflection, but you'll also see light pass through it. Anything that is transparent to some degree has a degree of transmission. And finally, reflection and scattering. This is when light is bouncing off of an object. So a lot of objects actually show or at least 3 of these particular characteristics. Go and take a look at a window. Sometimes you can see your reflection in it where light is bouncing off, but you can also see through the glass and actually experience transmission at the same time. So here we have a man who's standing very well dressed in a very Spartan apartment. This man doesn't seem to possess a lot in this apartment, but what he does have is quite varied. So he's standing in this apartment for some reason, probably because he doesn't have a TV or anything else to do, and here he is standing here, and the sun is emitting light. The sun emits light. As it hits the white snow, it will reflect this snow back. This is often referred to as albedo. The sun is referred to having a high albedo, and the ground here as low. The ground will absorb radiation and heat up, whereas the snow will reflect radiation back into space. The sunlight is actually coming in here and it's hitting this tree, and the tree is actually absorbing all wavelengths, all colours, because different colours are different wavelengths. It's absorbing all different wavelengths apart from green, which it's reflecting. That means the mechanism of photosynthesis here needs all the radiation from the sun except green. The sunlight is emitted this way, comes through this window, allowing transmission, and then is incident on this person's body. This means this very fine blue vest here is actually absorbing all wavelengths of radiation apart from blue, which it is reflecting back. He also has a light bulb in here which is emitting white light. This will bounce off of the mirror in reflection, and the light that's hitting this chair will be reflected and scattered in the red, but it will absorb all the other wavelengths of light coming from this lamp. So that's our emission, absorption, transmission, or reflection. If an object is transparent, it's considered opaque, and it will absorb light and it will allow light through it. If light comes through it, it's optically thin. If light is completely blocked by it, it's optically thick. So as I said, we saw a plant there, and plants are generally green. Not all, but mostly green. And plants tend to absorb all the wavelengths of light coming from the sun except green, which they reflect back, which they don't need to generate their energy. So plants tend to reflect 510 nanometer wavelengths. And this is useful for scientists if they are looking at, say, another planet and saying, is there any life there? Well, we know there's no vegetation on anything else in the solar system because we don't see any great reflection at 510 nanometers like we do when we put a satellite over the rainforest. Plants reflect what they do not need and absorb the rest. So why are we taking an aside to discuss light and temperature in so much detail? Well, the spectrum of a specific body tells you what maximum wavelength that body is emitting the most radiation. Now, this is crucial to systems such as cell phone cameras, infrared detectors, remote sensing. More and more systems are utilizing this particular nature of light than ever before. And that means as these things come into everyday life, we should really understand how they operate. So this is a little more of an aside than, say, the book is doing, but I want to go into this because this is going to be extremely useful. So if we look at this graph, this is the wavelength of light in nanometers. This is the ultraviolet end, and this is the infrared end. This is the heat end of the spectrum. Over here, this is the intensity per square meter of the object's surface. So this is how much radiation is coming off of the surface, and this is the wavelength of that radiation. Now this is mostly stars, and these examples are put in here because they're so bright, and, as it happens, fortuitously, slightly different colours. So, over here we have a blue star. The peak wavelength, that's the wavelength at which it's putting out most radiation, is right here, approaching 10 to the 2. This blue star is putting out radiation mostly towards the ultraviolet. Let's take this red star next, 3000 Kelvin, which for a star is relatively dim. Now, here it is as a red star. Red stars, it turns out, are not as hot as yellow stars like the sun. So here it is at 3000 Kelvin, and here is its peak wavelength. This is the wavelength that is putting out most radiation. And here's the sun, which is generally considered to be a yellow star, and here's its peak wavelength right here in the yellow. So the sun, being a yellow star at 5800 Kelvin, has its peak wavelength here. This means that the wavelength, the maximum wavelength that a star is putting out most of its radiation, tells you the color of that star. Now humans if we look at humans, you can really see other people by reflected light. Light is coming in, bouncing off their skin and coming to your eyes. We're not very luminous in the visual. In the dark, it's difficult to see people. But if we look at a human in the infrared, they will essentially glow as per some of the pictures we saw before, or watch the movie Predator. So here we are, a human, which is a mammal, which all radiate at about 310 K. We all have a temperature of about 310 Kelvin, unless of course we have a fever. Now, that means that our peak wavelength that we are emitting, not reflecting, but emitting light at, pumping out light, is here at 10 to the 4 nanometers, which is in the infrared portion of the spectrum. And this is the particular portion of the spectrum that things like thermal imaging cameras actually utilize. So the detectors in those cameras, if they're looking for criminals, looking for people who are survivors in earthquakes or in floods, or if you're just scanning someone to see if they have a fever, they will peak at about 10 to the 4 nanometers here at a standard sort of 300 Kelvin temperature. And that means there's a specific wavelength that tells us the temperature of all of these objects. If an object is emitting light of a certain wavelength, then it must be a specific temperature. And that's by emission, not by reflection. And there's that graph in a little more detail. Here's the 310 Kelvin human, not nearly as hot as a star, so its graph is not as high nor as broad. So objects which are not as hot tend to be towards the infrared. Objects that are very hot tend to be towards the ultraviolet. And weirdly, this is called black body radiation. And I realize that sounds a little strange because if something's radiating, how can it be dark? And this is one of those circular kind of arguments. So if we have a cavity, such as a closed oven, and radiation is beamed into that cavity, then if it's completely black inside, then it should absorb all wavelengths of radiation. If something is black, truly black, it is absorbing all wavelengths upon it. So radiation goes into essentially a black box and is absorbed by it. If we keep pumping radiation into it, simple logic says that eventually enough radiation should be absorbed that it should basically self-destruct and go up in flames. But this does not happen. So the experiment is we take an oven, we cut a hole in it and shine light into it. Inside that oven it's completely black and it absorbs the radiation. What actually happens is it goes into equilibrium and some dominant frequency of radiation is emitted. So here's the experiment. Here's our cavity. Here's our object. Here's our oven. And we can beam radiation in, and that radiation will bounce around inside and be absorbed by the black walls. Now, the radiation will build up inside here and heat up this oven. What will happen next is instead of going up in flames, it will start to re-radiate this energy. Now, that doesn't mean it will start to glow, not until it gets very, very hot, but it will absorb, say, visual wavelength. So if this is yellow light that we're beaming in here, this oven will absorb all of that yellow light, but then re-emit it in terms of heat. It will re-emit it at a different wavelength. That means it is equilibrating. By conservation of energy, it can't create or destroy the energy that's going into it. Rather than let that energy build up to a point where it's destroyed, it at least at first starts to re-emit that radiation as infrared radiation, as heat. And that's what gives us this characteristic black body curve that we saw previously. The box that we just looked at would be down here in the infrared in a similar region to the human with a very, very similar profile. And that's why we call it black body radiation, because even though it's giving out energy, it's giving it out in the infrared in this case. Now, that means this black body is a perfect absorber. If something's a perfect absorber, and then it gets rid of that radiation, that then means it's a perfect emitter. So it absorbs all the radiation incident on it and re-emits it, re-radiates it at a different wavelength. So black body radiation means something's a perfect absorber, but also a perfect emitter. And so we can model the sun with those black body curves and by black body radiation, even though the sun is anything but black. So hotter objects emit more light at all frequencies per unit area and emit photons with a higher average energy. And because stars are near perfect emitters, we can use a blackbody curve to measure the temperature and the wavelength of light that we should expect to see from them. So we can work out the temperature and the frequency and the wavelength of the light we should see from specific stars. And that's why we know that blue stars are hotter and red stars are colder. So if we look at something like the sun, here we are at about a 4500 Kelvin curve, and there is the black body distribution. So we can model stars as a black body. The terminology doesn't seem logical at first, but we can. And there's a lot of these in astronomy. And figuring out the peak radiation and what wavelength it should come from is an entire field. But as I said, this is also very useful if we're hunting for people or we're trying to figure out whether someone is healthy or not. By looking at the peak wavelength coming from them, we can actually figure out what their temperature is just by looking at the light. And we can do that using something called Wien's displacement law. Lambda max being the peak wavelength, the wavelength that the body is emitting most of its radiation, is equal to B, which is a constant, over T, which is the temperature in Kelvin. Here's lambda max, here's that maximum wavelength, here's your temperature, and B is Wien's displacement constant, which is 2.8977865 exactly, times 10 to the minus 3 meter Kelvin. So our question is, if you take something like a star, which one is hotter? Well, if we put that into this particular equation, we can rearrange and we can figure out which one is hotter. A blue star is a shorter wavelength, so it's 475 nanometers. A red star has a longer wavelength of 680 nanometers. This means a blue star is hotter than a red star. So let's actually do that calculation. Let's calculate the surface temperature of a star that has a peak wavelength of 400 nanometers. So if we put our detector onto the sky, we will get a big reading at 400 nanometers. We said lambda max was B over T. We know what lambda max is. It's 400 nanometers. That's 2.99 times 10 to the minus 3 over T, because we have the constant B. If you don't know, you'd have to look it up. Rearrangement, relatively simple. T is therefore B over lambda max. Substitution, substitute in 400 times 10 to the minus 9 meters. Remember, nano is times 10 to the minus 9, giving us 7,475 Kelvin. So we now know the temperature of this star is about 7,000 Kelvin, and it'll probably be towards the blue end of the spectrum. The other equation we have is to find flux. The flux is how much energy per unit area an object is giving out. So if it was a star, we could find out how much energy per square meter is being emitted by the star. Another constant is introduced here called sigma. Sigma is 5.67 times 10 to the minus 8 watts per square meter per inverse Kelvin. So what this formula is really saying, because we've got a temperature here, temperature to the 4th power, is that the flux is proportional to T to the 4. And this constant here will give you a final numerical answer. So that means if you increase a body, say, by 2 here, so if we increase by a factor of 2, that'll increase by 2 to the 4, so it'll increase 16 times. So again, let's pick on a star and say calculate the flux with a peak of a star with a peak wavelength of lambda max equals 400 nanometers. We already know the temperature in this case. This was from our previous example. So you would have to calculate the temperature using lambda max equals B over T. And that's 7,475 Kelvin. The flux is sigma T to the 4. Substitute in for sigma, substitute in for temperature. You'll get 177 times 10 to the 6 watts per square meter, or 177 million watts. Which is a lot. But then again, we are discussing a star here. And this is the principle on which thermal infrared cameras are based. So when we're looking at thermal imaging of people entering a building, here we're seeing someone at 23 Celsius. Again, I much prefer Celsius. When we're looking at these infrared cameras, they are using this exact principle. They're using lambda max equals B over T. They're using F equals sigma T to the 4. And then they are putting that out to a computer, which is assigning a color palette to those different maximum wavelengths. And you are seeing the flux and you are seeing the maximum wavelength of emission from these people who are walking in front of the camera. And that's what happens when you come in the morning through those cameras. So another application of thermal infrared detectors is to look at the heat signature of objects and terrain. So if we are to say look for a person who's either hiding out or lost in a desert, we can look for our signature 310 Kelvin emission from that person, and as such fit these detectors to either a drone or a spacecraft and look for these particular signatures. Of course, there's a slight disadvantage that most mammals radiate at 310 Kelvin, and as such, telling the difference between a human and an animal can be difficult. Other things that infrared detectors can do is look at a surface. If we look at the cooling of a sand dune, its thermal inertia versus flat sand, or rock versus a sand dune, by looking at how it cools through multiple observations, we can actually tell what we're looking at. We can tell whether we're looking at loose sand or rock or what the terrain is made of. Also, we can look at thermal infrared spectra, which means we can look at the makeup of these different materials and differentiate water from trees and chlorophyll from creatures. So thermal infrared detectors are being used increasingly in spacecraft and in aircraft. And thermal infrared detection has been used on most planets in our solar system. Most spacecraft going to different parts of the solar system actually have thermal infrared cameras on them. So here's an example. We're looking for someone in the desert. It's human, so we'll assume they radiate at about 310 Kelvin. The temperature is 310 Kelvin. There will be a corresponding lambda max. So we're going to use a reconnaissance drone, as we saw in the previous slide, equipped with infrared sensors. What peak wavelength of radiation should we calibrate our infrared detector to search for? Well, we know the human from the question is going to radiate at about 310 Kelvin. We want to know lambda max. So this should lead you to this equation, the maximum wavelength of emission being B over T. Remember, B is a constant, T is the temperature. Substituting into the equation, B is 2.897 times 10 to the minus 3, T is 310. That'll give us 9.35 times 10 to the minus 6 meters, or 9.35 micrometers, or microns as they're often called. So now we know what frequency, because that is related to the wavelength, we should be looking at to detect this human. But there is a problem, as I said. A camel is also a mammal and probably radiates at about 310 Kelvin. So how would we tell the difference between a camel and a human? And the answer is the flux. Now, a human will put out a specific flux. That's its energy per square meter. Now, if we were to see a camel, it will put out the same amount of energy per square meter, but camels tend to be relatively large creatures, and so will put out more energy overall. So what we really want to find is what will be the flux of this particular fugitive. Well, lambda max is 9.35 microns, we know this, and flux is sigma t to the 4. So do we need lambda max? Not necessarily. Our temperature is 310 Kelvin. So the temperature gave us lambda max, it's also going to give us the flux. Substitute in, sigma again is another constant of 5.67 times 10 to the minus 8. Our temperature is 310 Kelvin, and that means our flux will be 523.6 watts per square meter. So if we had a much larger flux coming from our creature, we would actually know that it was due to the fact that it's a bigger creature.